Optimization problems are also known as minimum and maximum problems since they help you determine the minimum and maximum values. So you can use them to determine questions that ask for greatest profit, least cost, least time, greatest voltage, optimum size, least size, greatest strength, greatest distance, and so forth. So in this section, we'll be looking at how to find maximum volume, and the process for this is to just set up a primary equation. So in this case, a manufacturer wants to design an open box containing a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So the primary equation, or the equation that gives a formula for the quantity to be optimized or minimized and maximized, is volume is equal to x squared times h, which is just length times width times height. And drawing a picture is very helpful in solving these questions. So after you write that equation and you make that your primary equation, then you need another equation that will help you eliminate one of the variables, either x or h. So since it gives you the surface area, you can use that as your secondary equation. So surface area is equal to the area of the base plus area of four sides. So 108 is equal to x squared plus 4xh. 4 for each side. So because you want to maximize the volume, you want to write volume as a function of just one variable. So in order to do this, you need to write x squared plus 4xh is equal to 108 for h in terms of x to obtain this value. And then you need to substitute this value into the primary equation for h. So after you do that, this should be your new volume equation. Then you need to figure out your domain. So 0 is less than or equal to x, which is less than or equal to the square root of 108. That is your possible domain because x can't be less than 0 and it can't be greater than the square root of 108. So after you do that, in order to maximize the volume, you need to find the critical numbers of the volume on this interval. So take the derivative of the volume equation and you get this, and then you set that equal to 0, and then solve for x values. And in this case, x is equal to plus or minus 6. So you know that x can't be less than 0, so negative 6 is not an answer. So therefore, you need to find the volume of x of 6 and then 0 and square root of 108. So you get 0 for a volume at 0 and then 0 for a volume at square root of 108. So the volume when x is 6 is 108. So volume is maximized when x is equal to 6. And the dimensions of the box are 6 inches by 6 inches by 3 inches. So there are some guidelines for solving applied minimum and maximum problems. First, you need to identify all given quantities and all quantities to be determined. If possible, make a sketch. And as I said earlier, a sketch is really helpful in solving these problems. Then you need to write a primary equation for the quantity to be maximized or minimized. Then reduce the primary equation to one having a single independent variable. This may involve the use of a secondary equation relating the independent variable of the primary equation. Then determine the feasible domain of the primary equation. That is, determine the values for which the stated problem makes sense. And then determine the desired maximum or minimum value by the calculus techniques learned before, whether through critical points, max and min with second derivative test, first derivative test, and so on. So you can also use max and min for finding minimum distance. Same for maximum distance, vice versa. For finding area, for finding minimum length, and an endpoint maximum. So let's do an example where we work with finding minimum length, because usually those are a little bit trickier than the area and volume ones. Okay, so let's do this one. Two posts are 12 feet high. Two posts, one 12 feet high and the other at 28 feet high, stand 30 feet apart. They are to be stayed by two wires attached to a single stake running from ground level to the top of each post. Where should the stake be placed to use the least amount of wire? So first, I already drew a little diagram, and this is the 12-foot pole and this is the 28-foot pole, and it's 30 feet in between. So we know that much, and we know that there are going to be two wires that are running from the tops to a stake, and this is the stake, this point here. So then you need to label your picture, and you know that this whole length is going to be 30, so I designated this length as x and this length as 30 minus x. So then you need to find the hypotenuse, which is the actual length of the wire, and you need to do that for both because that's the total length of the wire. So 12 squared plus x squared is equal to this length squared. So you take the square root of 12. 12 squared plus x squared is equal to this value, I'll just designate as z. So then, z squared, excuse me. So then z is equal to the square root of 12 squared plus x squared. And I already wrote that there, and that's 144 plus x squared. And you do the same thing for this side. So 30 minus x squared plus 28 squared is equal to, I'll call this y squared. So that means y is equal to the square root of 28 squared plus 30 minus x squared. Okay, so then we need to find the minimum. We need to find where we should put the stake to get the least amount of wire. So we're trying to minimize the length of the wire. So the length of the wire is equal to z plus y, these two values. And that is equal to square root of 12 squared plus x squared plus the square root of 28 squared plus 30 minus x squared. So this is the length that we want to minimize. Now, since there isn't a second variable, we don't need to get rid of one of the variables here since we only have constants and x's. So then we can immediately take the derivative of this. So the derivative of the length, I should indicate that length L is equal to length of wire. Okay, so the derivative of the length is equal to x over square root of 144 plus x squared plus x minus 30 over square root of 28 squared plus 30 minus x squared. Okay, next you need to set the derivative equal to 0 because you're trying to find the minimum. So you set that equal to 0, and then you can cross multiply. So x minus 30 times square root 144 plus x squared is equal to the square root of 28 squared plus 30 minus x squared times x. And then square both sides so you get rid of the radicals. And you get x minus 30 squared times 144 plus x squared. And that's equal to, and when you expand this out, you get 1,684 minus 60x plus x squared times x squared. You get that, and then you need to keep on expanding. So you get, on this side, x to the 4th minus 60x cubed plus 1,044x squared minus 8,640x plus 129,600, and that is equal to 1,684 x squared minus 60x cubed plus x to the 4th. Then you just need to simplify everything, so the x to the 4ths cancel out, the 60 to the x thirds, And then this also simplifies. Or 1 second. You simplify everything down. Let's see what else simplifies. Okay, so then move everything to one side so you get 0 on the end. So you get 640x squared plus 8,640x minus 1,209, and that's equal to 0. Then you can factor this out, factor 320 out, so you get this. So now our critical values are x is equal to 9 and x is equal to negative 45 over 2, or negative 22.5. So we need to determine what the domain of our x is, and I should have done this sooner, but so the x value cannot be less than 0, so that's the minimum value, and then it also can't be greater than 30, because if it's greater than 30, then that means it's greater than this distance, and that's not possible. So 30. So this value is negative, so that means it's not in our domain, so this can't be an answer. So that means we're left with x equals 9. So x equals 9 is the distance that it should be placed away from this point, from the 12-foot pole. So just to confirm it, we should, when you take the length of the wire when x is equal to 0, you get about 53.04, and when you do it for 9, you get 50, and when you do it for 30, which is the maximum value, you get 60.31. And you need to check the endpoints just to make sure that your value is the minimum or the maximum. And in this case, it is the minimum. So 9 feet is the minimum distance that the stake should be placed in order to minimize the length of the wire.